Hello and welcome back. This is lecture 13 of analog integrated circuit design. In the previous class we looked at a simple realization of an op amp at the level of the control sources. We realized it using a voltage controlled current source loaded by a capacitor. We also saw that the output resistance of the voltage controlled current source limits the DC gain, and this consequently results in steady state error. So, even after a long time the output does not reach exactly the desired value, but will be a little bit away depending on the amount of DC loop gain. Okay. So, the DC loop gain has to be higher than a certain value, and this requires us to have different op amp topologies which can possibly realize higher and higher DC gains. In this lecture we will look at one such op amp which will perform better than the one that we saw in the previous class. The op amp that we had was a voltage controlled current source or a transconductor loaded by a capacitor, and to isolate the external load we can use a buffer, but it turns out that buffers are not very easy to implement in CMOS technology. So, they can be implemented, but they bring with them their own limitations. We would like to avoid them. So, most of the time op amps are used without explicit buffers in CMOS processes. This is the input voltage and a current GMVE is pushed out of it. So, the voltage here will be GM by SC times VE, where this is the capacitor C. So, the unity gain frequency of this op amp omega u equals GM by C. Okay. Now, even if the buffer isolates the external load, the transconductor has an output resistance R naught or an output conductance G naught, okay, which are reciprocals of each other. Now, this is an inherent property of a voltage controlled current source. Just like a current source has an output resistance which is not infinite, a voltage controlled current source also has an output resistance which is not infinite. So, because of this the transfer function that we will get will be the output by input of the op amp should have been GM by SC, but this is not what we will get. We will get GM by SC plus the output conductance. This can be written in various forms. We can write it as GM R naught divided by SC R naught plus 1, which makes the DC gain explicit. At DC or low frequencies we have a gain equal to GM R naught, and the pole which was at the origin in this transfer function has moved to a frequency minus 1 over C R naught. Okay. It can also be written in an alternative form as 1 by SC by GM plus 1 by GM R naught. Let me write it on the side. Now, in this case this is the ideal part that we would like to implement. Additionally, we have a small non ideal number here 1 over GM R naught. So, the higher the value of R naught, the higher the DC gain GM R naught, and the smaller will be this non ideality. Okay. But in general you will never be able to make this infinite. So, we will have to live with some finite value of GM R naught, and in fact depending on the topology that we choose, the value of GM R naught may be limited to some modest value like 50 or 100 or so. Okay. Whereas sometimes we would like to have op amps with the gains of 10,000 or even a million. So, there are limitations on how high GM R naught can be. Okay. Now, this depends on the topology. So, depending on the topology we could have either 25 or 250, but there will always be some limitation. Additionally, what happens is that sometimes Let us imagine a case where the op amp is used without a buffer. Okay. And let us also assume that there is a resistive load R L. Now, in this case the DC gain of this op amp will be G M R naught parallel R L, and regardless of how high you make R naught, you will always have R L. So, the DC gain will be limited to G M times R L. Okay. So, this is another problem, that sometimes when you have resistive loads, the DC gain will be limited by that, and we have to find ways of obtaining higher DC gains even with external loads. Okay. So, basically there are different possibilities of trying to increase DC gain. First is increase R naught, that is, we do something to the transconductor so that its internal resistance is increased. Now, this clearly does not help when we have an external resistive load R L, and we may have to use alternative topologies. Okay. So, during the initial analysis we will still assume that there is no external load. We will derive the topology and then show that even with external resistive load these things can work well. Okay. Now, to investigate alternative topologies, first we need to find out exactly why this topology results in limited DC gain. It is quite simple. Ideally we would have wanted all the current from this transconductor GM to flow into the capacitor C. Now, what happens is when you have R naught, a part of it flows into it. So, that is why we get a finite DC gain, as opposed to when we had only a capacitor we would have infinite DC gain and we had an ideal integrator. Okay. Now, essentially what we are doing here is converting the output current GMVE of the transconductor into a voltage by passing it through a capacitor. Okay. Now, if we find a different way of converting this current to a voltage Gm by SC without having some of the current going to some other component, we will make a better integrator. Okay. So, that is the problem. Now, that is a well known problem which also has a well known solution. The problem basically is that let us say you had a current I naught going into an impedance Z, and the current source has some internal output resistance R naught. What happens is a part of this current will go into that. Okay. So, the output voltage instead of being I naught times the impedance Z will be I naught times Z parallel R naught. Okay. And the way to get around it is not to simply try and pass the current through a load resistance by applying the load across the current source, but to make what is known as a current controlled voltage source. And we have already seen the topology of a current controlled voltage source using an op amp, and for now let us assume that the op amp itself is ideal. I naught, and I connect the same impedance Z in feedback. Okay. And initially let me assume that the op amp is ideal. What does it mean? This voltage is 0 and the output voltage will be exactly equal to I naught times Z, assuming that op amp is operating in negative feedback. Now, what happens if the current source is non ideal and we have a resistance R naught? Because this voltage is 0, no current flows through the resistance and all of the current I naught still flows through this impedance Z. Okay. So, even in presence of R naught, the output voltage will be I naught times Z. So, that is why when you want to convert a current to a voltage, it is better not to simply apply the impedance across the current source, although that is possible. It is better to use a current controlled voltage source of the appropriate trans impedance value. Okay. You can clearly see that the problem at hand for us is also the same. We have a current GMVE which has to pass through a capacitive impedance. Now, we were simply applied the capacitance to the output of the transconductor. That is not what we should do. We should try to make a current controlled voltage source whose input is the output current of the transconductor and whose output voltage will be the output of the op amp. Okay. We will see how to do that. Now, before we go there, one more thing to keep in mind is that of course, we will not have an ideal op amp, we will have a real op amp with some unity gain frequency omega u. Okay. Now, what is the range of frequencies over which this behaves like a current controlled voltage source? Behaves like a current controlled voltage source over a range of frequencies where the loop gain magnitude is much more than 1. This we have seen earlier. Rather, basically it is a range of frequencies within the unity loop gain frequency of this particular feedback loop. Okay. This is a very important point. This op amp will be a real op amp and it has to be such that its unity gain frequency is higher than the frequency of interest. Now, what is the frequency of interest for us? We would like this our op amp to behave like an integrator over a certain range of frequencies, and the unity gain frequency of the op amp which is used to make the current controlled voltage source has to be much higher than the unity gain frequency of the op amp we are trying to realize, that is Gm by C. Okay. We will see all of these things in more rigorous analysis later, but it is a good idea to get an intuitive feel for how things should be when we design them. So, how do I make my op amp? Instead of simply loading the transconductor with a capacitor C, I will not do this. I will pass it through a current controlled voltage source whose transimpedance is C. Okay. With a transimpedance of 1 by S C. Now, with an ideal op amp, the voltage here will be 0 and the output voltage will be, I have a current GMVE here. So, the output voltage here will be minus Gm by SC times V. Okay. The sign inversion comes because simply because of the inversion through the second stage. So, to get rid of that inversion, what I will do is I will invert the signs of the transconductor. I will have minus plus, so that I have GMVE flowing that way. It will flow in the same way through the capacitor and the output voltage will be plus Gm by SC times VE. Okay. Obviously, this op amp will not be ideal, because if we had an ideal op amp, we would try to just use it and not make another op amp with it. Okay. So, this will be some real op amp, and we have to make sure that even with the real op amp, all our assumptions hold. Okay. Now, what is the op amp that we know? There is only one op amp that we know so far, and that is this particular op amp. Okay. So, this is the op amp that we used in the previous lecture, discussed in the previous lecture, and this is the only op amp that we know. So, we will just use it in its place. Okay. So, please understand what is going on here. We want to make an op amp. So, we will instead of loading the transconductor with a capacitor, we will follow the transconductor using a current controlled voltage source. But to make the current controlled voltage source, we need some op amp. So, we will use the simplest op amp that we know, which is basically a transconductor which is loaded by a capacitor. Okay. So, if we do that, what do we get? This is the op amp used to make the current controlled voltage source. And I will call the CL CL will be any capacitance that is loading the transconductor plus any external load that may be applied to the op amp. Okay. So, that will always be present. So, all of that is clubbed into a single capacitor CL. I have VE here, I will call this GM1 and I will call this GM2 just to distinguish between them, and also invariably between any node and ground there will be parasitic capacitance. Between the output of the first transconductor and ground there will be some capacitance which I will call C1. In analysis we need to include the effects of all of these things and finally figure out what exactly happens. So, the reasoning so far has said that this op amp will be better than using just that one, that is GM1 loaded by a capacitor C. Okay. So, that is the reasoning by which we derived all this, and also let us put the limitations in place. Each transconductance will have some output resistance. Like I said earlier, you cannot make a current source with an infinite output resistance. You can also not make a transconductor or a voltage controlled current source with an infinite output resistance. Okay. So, this is the topology that we have to analyze and see if it is really better than what we started off with, which is that one. Okay. I will redraw my op amp here. Okay. We need to do analysis of this and find out the ratio of output voltage to the input to the op amp VE, and that will be the transfer function of the op amp. Now, before we go and do the full fledged analysis, it is a good idea to look at the circuit and see what the transfer function might come out like. Okay. This will serve later as a sanity check for us. Now, what will be the order of this transfer function? How many poles will it have? The number of poles or the order is nothing but the number of independent state variables in the circuit, and state variables are nothing but capacitor voltages and inductor currents. Here of course, we do not have inductors, so it is only capacitor voltages, and we have 3 capacitors connected like this. So, there can be at most 3 state variables, but we also see that the voltage on C1 plus the voltage on C equals the voltage on CL. Okay. The 3 capacitors are connected in a loop, which means that only 2 of them can be independently set. So, there are really only 2 independent variables. So, that means that this will be a second order transfer function, that means there will be 2 poles. Now, there can also be any number of zeros, that is a little harder to figure out. We will see later how to look at the circuit and try to figure out the frequency of the zeros, but one guideline is that whenever you have 2 parallel paths from, let us say, the output of the first stage to the final output, there is a path through GM2, there is also a path through the capacitor. In general, you can expect zeros in such a case, and so we will also expect that there will be a 0 here, but this is a little more vague, and it is also possible that you do not have a 0, or there may be zeros even without 2 parallel paths and so on, but that is some expectation that we have. Okay. And finally, what will be the DC gain of this? Again, when we find out the transfer function and set the value of S to 0, we should get the DC gain. Okay. Now, we can also find the DC gain independently without doing the full blown analysis with Laplace transforms. If we do that, then we can, after we do the analysis, we can compare it to this value and see if it satisfies sanity check or not, and that is again extremely simple. For DC, all that happens is that all these capacitors are open circuited, C1, C and Cl. We have a current GM1 times VE going into RO1. So, the voltage here will be GM1 RO1 VE, negative of that, and that is applied to the second transconductor, which provides a current GM2 times that voltage, which flows into the output resistance RO2. So, the output voltage will be plus GM1 RO1 GM2 RO2 times VE. It is basically a product of the DC gain of the first stage and DC gain of the second stage. This is something that you would easily expect. When you have a cascade of stages, you will have the product of DC gains to be the total DC gain, and that is GM1 RO1 GM2 RO2 in this case. Okay. So, now let us do the analysis. This circuit has two nodes, and by writing KCL equations at these two nodes, we can find out all the voltages and currents in the circuit. First of all, KCL at this node, let me assign this node voltage to be some V1, and this is of course V0, and I will write it in a matrix form, some admittance matrix times the vector of voltages V1 V0 equals the vector of source currents, that is currents flowing into these nodes. First of all, the current flowing into this node containing V1 is minus GM1 times VE. Okay. This is provided by the first transconductor, and the matrix entries can be filled up. This entry here is the total admittance, which is S C1 plus C plus GO1. GO1 is the reciprocal of RO1. It is convenient to use the conductances directly instead of writing it as 1 over RO1 everywhere. Okay. And this term is minus SC. Basically, the current through this capacitor is SC times V1 minus VO. That is why we get plus SC here and minus SC. Okay. This should be familiar to you from basic circuit analysis. Now, similarly, the entry here is the total conductance at the node containing VO. So, that is S CL plus C plus GO2, and the entry here is the current being drawn from this node due to the voltage on that node, and that happens due to two components, one is C and the other one is GM2. Okay. It turns out that we will get GM2 minus SC here. Okay. So, this is a system with two nodes and there are two equations, and by solving for this we can find out the value of V0 in terms of VE. Okay. And there are any number of ways to solve this. You can invert the matrix and so on, but since we are only interested in the output variable, we will use Kramer's rule, which says that the output voltage V0 will be equal to the determinant of this matrix when the second column is replaced by the source vector divided by the determinant of the admittance matrix. Okay. So, let me copy this over. So, as I said, I need to, I will copy this over again. So, as I said, V0 is nothing but the determinant with the second column replaced by the source current vector, that is the determinant of that, divided by the determinant of the admittance matrix. Okay. And this gives you it is the determinant of what is on top on the numerator, and the determinant of the denominator is nothing but we will have a number of terms containing s square due to the product of this and that, and also due to product of this and that. Okay. This much is due to the product of this one and that one, minus I will have s square times c square. Okay. And in fact, this cancels with that one, and we will have a number of terms containing s, that is due to product of this with this, product of this with that, the product of this with that one. And the terms turn out to be okay. And in addition to these, there will be a constant, and that is only due to this one and that one there. So, that will come out to be GO1, GO2. Okay. So, let me just rewrite it, and also I will take VE to the left hand side, so that I get the transfer function V naught by VE. This will be equal to GM1 GM2 minus SC divided by the second order term first, C1C CCL plus CL C1 plus the first order term, which has okay, plus the constant term. So, this is the transfer function of the op amp. Looks somewhat complicated, but it turns out that we can make intuitive sense of this transfer function as well. But first of all, the sanity checks. What did we say? The DC gain. What is the DC gain here? If I substitute S to be 0, this goes away and all these things go away. So, okay. So, that is one thing, and this is exactly the value that we got. We said the DC gain was GM1 RO1 times GM2 RO2, and that is exactly what we have here, except that it is written in terms of conductances, that is all. And also we said that it is a second order transfer function, because there are only two independent state variables, and that is the case also. There are two poles and there is one 0, okay. We can see that in the numerator there is one 0, and this also we guessed because there were two different paths to the output. From the output of the first stage to the output of the second stage, there were two paths, one through the transconductor GM2, one through the capacitor C, and generally when you have two parallel paths to the output with different phase shifts, different frequency dependencies, you will end up getting a 0. Okay. So, the next thing is to figure out where the poles and zeros are, okay, and then try to make sense out of them. So, first of all, the 0 frequency is very easy. Where is the 0 here? It is when the value of S for which this term becomes 0, and 0 I will denote it by Z1 equals plus GM2 by C. Okay. I explicitly write the plus because zeros can be in the right half or left half plane, and this happens to be in the right half S plane. Okay. Now, the poles of course can be obtained by solving this quadratic equation, but the conventional solution to the quadratic equation, the familiar one, minus b by 2 plus minus square root of b square minus 4ac by 2a, that simply will not be able to do here, because each of the coefficients a, b and c are quite complicated, and if I even manage to write down that expression, we will not be able to make any meaning out of that. Okay. So, what we will do is we will find some approximate ways of solving the quadratic equation. It turns out that there is an easy approximation which also in this particular case yields intuitive results. Okay. So, it turns out that the quadratic equation of course has two roots, but when the two roots are very far from each other, that is when the magnitude of one of the roots is very small compared to the magnitude of the other root, the following approximation can be used. Okay. Let us say we have a square plus bs plus c equals 0, and there are two roots s1 and s2. Okay. So, this clearly means as1 square plus bs1 plus c is 0, and also as2 square plus bs2 plus c equals 0. Okay. And let us assume that the magnitude of S1 is much smaller than the magnitude of S2. You can verify this for yourself. You can write down the expression for the solution of the quadratic equation and see that this is indeed the case. And in this case, it turns out that first of all, for S1, this term will be negligible compared to BS1 and C. Okay. So, this is approximately equal to 0, and we can easily determine S1 to be approximately minus C by B. Okay. What we have done is to reduce the quadratic equation to a first order or a linear equation. Similarly, for S2, it turns out that this is much smaller than the other two, and S2 can be approximated by minus B by A. Okay. Again, we had to solve only a linear equation. Now, you have to keep in mind of course that this is true only when one of the magnitudes is much smaller than the other. Now, in fact, you can try solving every quadratic equation that you see approximately like this and see if it is indeed true that one of the roots has a much smaller magnitude than the other. If it is, then it is consistent, otherwise it is not. Okay. Once you follow this procedure and find the roots, S1 must come out to be much smaller of magnitude than S2. Now, clearly this will not hold when the quadratic equation has complex conjugate roots, because when you have two roots which are complex conjugates of each other, the magnitudes of the two roots is exactly the same. So, this will hold only for real roots which are very far from each other. Okay. So, this at least looks manageable given the complexity of the coefficient A, B and C. Okay. So, now let us find out the values of these. I will call this pole P1 to be the smaller one, and that is nothing but minus C by B. Okay. And this, if I substitute the coefficients from my quadratic equation, what do I get? So, this is the expression we have. This is still somewhat complicated, but as you will soon see, you can make intuitive sense out of this one. I will just divide both numerator and denominator by GO2 to put it in a more meaningful form. The reason I did this is to get the answer in the form of some conductance divided by some capacitance. As you can see, the numerator has some conductance GO1 and the denominator has terms which represent capacitances. We will later make sense of what these capacitances are. Okay. Similarly, the higher of the two roots, the higher frequency root P2 will be minus B by A, which is minus okay, and here we will have and in this particular case I will divide both the numerator and denominator by C plus C1. Okay. Again you will later see why this makes sense. So, first of all I will have C by C plus C1 times GM2 in the numerator. You see that GO2 is multiplying both C and C1. So, we will have plus GO2 and plus we will also have GO1 C plus Cl by C plus C1. Okay. And in the denominator I will have Cl okay, plus C1 C divided by C plus C1. Okay. So, again I have made some manipulation of the expression, so that in the numerator I have a conductance and in the denominator we have a capacitance. Okay. So, that makes it easier to make sense out of the poles. Now, before we try to do that, let us first quickly review how one might be able to tell the values of the poles in a circuit intuitively without doing circuit analysis. Okay. So, let us take the simple op amp we had earlier. Let me just call the capacitance C1 and this conductance GO1, that is simply the output resistance of this conductance GM1. Okay. Now, you can work this out and see, right, and you will find that the pole is at minus GO1 by C1. I will not do the analysis here. And similarly, you can let us say add another stage here. Let us say this is a transconductance GM2 and this is a conductance GO2 with a capacitance CL. Okay. Now, you can work this out. It turns out that you will have some transfer function from here to there and another one from here to there, and the two are independent. That is, the first one has a transfer function GM1 by GO1 plus SC1. The second one has a transfer function GM2 by GO2 plus SCL, and the final transfer function is the product of the two, and there will be two poles. Okay. And the second pole is due to the second stage due to this combination. The first pole is due to that one GO1 by C1. Okay. And there will be another pole at minus GO2 by CL. Okay. So, in circuits where you have these RC parallel combinations which are isolated from each other, you can identify the poles to be simply minus the conductance divided by the capacitance across it. Okay. So, you identify capacitors, you find what conductance appears across them, and the ratio of conductance to capacitance gives you the poles. And you must have done this in basic circuit analysis also with simple RC circuits, and exactly the same thing holds in this case. Okay. Now, when you have capacitance and resistance connected in arbitrary fashion, this is not easy to do or maybe even impossible to do, but when you have isolated pieces of R's and C's, you can do this. Okay. Now, you also notice that the example circuit I took is exactly the same as this op amp, except that I did not have this C. Okay. In my refined op amp, what I think is the refined op amp, I also have this capacitor C. Okay. Now, without that C, we can identify the poles very easily. Now, with C, we have identified the poles to be this one and that one. Okay. Now, we will try to relate the case without C and with C and see how it makes sense. Okay. So, also notice that this pole has a conductance G01 and some capacitance, and here it has a conductance G01 and a capacitance C1 which is across it. Similarly, this has G02 plus some conductance divided by some capacitance, whereas here we have G02 divided by Cl. Okay. So, without C I have minus G01 by C1, and with C I have minus G01 by C, Gm2 by Go2 plus 1 plus Go1 by Go2. Okay. Plus C1 plus Cl times Go1 by Go2. Now, we can already see some relationship between the two. We have Go1 by C1 plus some capacitance, and what is that capacitance? That is C times Gm2 by Go2 plus 1. Okay. Now, why do we get a term like this? If you observe, the second stage looks like this one. It also has this capacitor Cl. For the moment, let us ignore this capacitor. So, basically from here to here, from here to the output, there is a gain of minus Gm2 by Go2, and this capacitor C is connected across an amplifier whose gain is minus Gm2 by Go2. Okay. So, let us say I have an amplifier of a negative gain minus A, and I connect a capacitor across it. What happens? And let us say I apply some test voltage to the input. The output will be minus A times V test, and the voltage across the capacitor in this polarity will be A plus V 1 times, sorry, in this polarity will be A plus 1 times V test. So, that means that from this source V test it will draw a current which is equal to A plus 1 times V test times SC. Okay. So, simply looking into this block, it appears like I have a capacitance of A plus 1 times C, because if I apply V test to this, the current flowing here would be exactly same as that one. Okay. This phenomenon is known as Miller effect. If you connect a capacitor from the input to output of a negative gain amplifier, from the input it looks like a much larger capacitor, and how much is it? It is equal to 1 plus gain times the capacitance value. Okay. And this capacitor is also sometimes called the Miller multiplied capacitor. Okay. Now, the second stage of our op amp has a negative DC gain of Gm2 by Go2. We have a capacitor C connected across it. So, looking in here, it approximately looks like a capacitance of Gm2 by Go2 plus 1 times C. Okay. It is only approximately so, because the amplifier we have here is not ideal. Okay. It is not an ideal voltage controlled voltage source of this gain, unlike this one. This is a ideal voltage controlled voltage source of gain minus A, whereas here it is a transconductor loaded by a resistor. There is also a capacitor here and so on. So, only approximately it looks like a capacitor. So, you do see that in addition to C1 which appeared across Go1, you also have this particular term. Okay. So, in other words, if I redraw the complete op amp, this is the first stage, C1 appears directly across Go1, and we have this capacitor across an amplifier whose DC gain is Gm2 divided by Go2, and there is also some capacitance Cl here. So, approximately looking into this, we see a Miller multiplied capacitance C times Gm2 by Go2 plus 1. Okay. So, what do we have? We have a conductance Go1 that is there, we have a capacitance C1 that is there, and we have a Miller multiplied capacitance which is there. Now, there are also these other terms, okay, this one and that one. They appear because first of all this pole itself was obtained approximately, and secondly that is as an approximate root to the quadratic equation, and secondly this amplifier is not ideal. Okay, it has a finite output resistance, I mean non-zero output resistance and so on. So, you also have these extra terms, but it turns out that the significant terms are what is highlighted here, C1 and the Miller multiplied C. Okay. So, although the expression was complicated, we were able to make intuitive sense out of it, which is good. So, what happens is that we will have across the conductance, output conductance of the first stage, we effectively have these two capacitors, capacitance C1 and the Miller multiplied capacitance C, because C is connected across the input to C is connected from the input to output of the second stage. Okay. Now, it is also of interest to see what has happened to this pole frequency. Has it increased or decreased? What do you think? So, you can see that first of all it is obviously reduced in frequency because the numerator is the same, the denominator C1 remains as it is, and we also have this, and if C is comparable to C1, Gm2 by Go2 is a number that is much more than 1. So, the denominator has increased a lot. Okay. So, when you have no capacitor to when you have a capacitor, it moves to low frequency. Okay. Similarly, P2 which was minus Go2 by Cl became minus Go2 plus there were other terms like Gm2 C by C plus C1 plus Go1 C plus Cl by C plus C1, okay, and divided by Cl plus C times Cc by C plus C times C1 by C plus C1. Okay. The next lecture we will go and see, interpret this and then make sure that it makes intuitive sense as well. Okay. In the next lecture what we will do is we will make sense out of this expression as well and see how it makes intuitive sense. Thank you and see you again.